Alrighty, good afternoon, everyone. Thank you so much for joining us for today's webinar on Rolling Fork, Winona-Amory tornadoes 1 year later. I'm Christiana Allen. I am VORTEX-SE Outreach and Engagements Risk Communication and Learning Specialist. Um, Today's webinar will be recorded. So if you have to leave for any reason or you want to pass this information along, you will have access to that when we wrap up. Um, and we will also have Q&A. So we'll pause for Q&A after each set of speakers. And you can just put your question in the chat box. Um, if we're able to answer the question, we'll go ahead and answer it during the webinar, but if not, we'll be sure to follow up with an answer for you in your email. So be on the lookout for that if we're unable to answer it here. So without further ado, we're going to go ahead and get started, and I'm going to introduce Tracy, our first speaker.
Thank you, Christiana. Welcome. As Christiana said, my name is Tracy Sempier. I'm with Mississippi Alabama Sea Grant. I'm the Vortex Southeast Outreach and Engagement Coordinator. And I just wanted to give a quick background about why we're here and sort of the purpose of our webinar today. So Sea Grant has a partnership with the National Severe Storms Lab, and this partnership allows our extension folks here in Mississippi and Alabama to be able to take the research that's conducted at the Severe Storms Lab and translate that for on-the-ground target audiences. And so in our area, we have several vulnerable populations that we target, especially as it relates to tornadic activity. We want to make sure that we build relationships with the folks on the ground. Christiana and I meet in local libraries. We go to festivals, various events that we know folks are going to attend. We want them to be able to recognize our face and use us as a resource. And then if we don't know the answer to something, we go back to many of the folks that you see on this webinar today, and we ask and we try to get those answers for folks. Just to give you a quick idea of where we've been, let's see if this is going to come up for me. We have been around since 2020, so kind of started during COVID, and now we have worked in multiple states since then, but have really focused in Mississippi and Alabama. We have several partner organizations that we've developed over time, and we have conducted many trainings across both Mississippi and Alabama, and we've done some online events as well, just trying to reach people in a variety of methods. So in today's webinar, our goal is to learn a little bit more about those tornadoes that impacted the Rolling Fork, Amory, and Winona areas in Mississippi just a little over a year ago. And then we'd like for you to understand what has happened both with the physical science and the social science, because we did have scientists, researchers, and instrumentation deployed during these events. So we want to let you know what that looked like and what we've learned from that, and any future research that might be conducted and actions that we've taken as a result. And so these are our guest speakers that we've got with us today. We're super excited about. We've got Alan Gerard, Kenzie Krokak, Mike Caniglio, Tony Liza, and Cody Berry. And they're all going to be talking about their different specialties and sort of what they have been doing to look at these storms and find out what we can learn from them so that Christiana and I can do outreach in the future. So with that, I'm going to ask if Alan might be ready. And if you wanted to share your screen, Alan, let me stop sharing.
Let me unmute. And now let me get to the right place. All right. Share screen. All right. Can you see that?
Yes, we can see it. Perfect.
Okay, great. So I'm just going to start off with a very kind of high-level overview of this tornado event that the rest of my colleagues are going to be talking about today, and just a little bit about why we do some of the physical science work that we do. So we're really going to be focused on three particular significant tornadoes that occurred back on March 24th of 2023. The first one was the most intense tornado of the three, and that it impacted the lower Mississippi Delta through Issaquena, Sharkey, and Humphreys counties, and into Holmes County. The main city impacted was Rolling Fork, Mississippi, which is where most of the fatalities occurred. This tornado was a high-end EF4 on the enhanced Fujita scale, which goes from 0 to 5. It was really at the top. It was basically rated as high as can possibly be rated without it being an EF5. There were 17 fatalities and 165 injuries with this tornado. It was a particularly long track tornado. It was on the ground for over an hour, and it produced nearly $100 million in damage, primarily in Rolling Fork, but then also Silver City, which is a smaller community northeast of Rolling Fork, also had significant damage and impacts as well. So the second tornado we're going to talk about is the Black Hawk-Winona tornado. Winona is the primary city that this tornado impacted. Luckily, it went just to the south of Winona. It impacted just kind of the south side of Winona rather than going right through town, which was very lucky. Black Hawk is a small community in Carroll County, which is the county kind of where this particular tornado started. This tornado was rated an EF3 with max winds of 165 miles an hour. It caused 3 fatalities and 5 injuries, and it was on the ground for about a half an hour. But as you might suspect from looking at the way the track is, it was produced by the same supercell thunderstorm that produced the Rolling Fork tornado farther to the west. And then the last tornado was the Amory tornado, which, again, from the same supercell storm or the same general supercell storm, developed and produced a tornado that impacted, and I'm looking at my colleagues, I'm pretty sure it impacted the west and north side of the Amory community, producing almost $80 million in damage, 2 fatalities and 55 injuries, and it also was on the ground for about a half an hour. So this series of 3 tornadoes, if you just kind of add it up, caused 22 fatalities, over 200 injuries, and nearly $200 million in damage. I was actually the meteorologist in charge for the Jackson, Mississippi office for a number of years before I came to the National Severe Storms Lab, and this certainly, is at the top end of some of the significant Mississippi tornado events that have occurred over the years, and that's saying something, because Mississippi has had some of the worst tornado disasters in U.S. history. So the fact that this series of tornadoes is at the upper, is in the upper echelon of tornado events for this region, is really says something, and kind of goes to why not only we were there to study it, we knew that there was potential for this sort of an event, but also why there's been so much focus on it in the year and a half since. So I want to just spend a few minutes here now as we lead into the next talk, discussing, kind of what we're trying to do here in the southeastern United States with our physical science research. Vortex Southeast really got started with an idea of trying to look at some of the ways in which tornadoes in the Southeast have differences than their counterparts in the plains. Tornadoes had been very well studied over the years through a lot of field projects and a lot of other campaigns dating back, to the 70s. The Southeast is a much more challenging area to try to do physical science field work in, because there's a lot more terrain issues. There's a lot more forest and trees that reduce visibility. The tornadoes tend to move much more rapidly, and all of those things make it much more challenging. But there are a lot of unique aspects to tornadoes in the Southeast that make it worth the effort. There is a lot more because of the terrain and differences in roughness, because of forestation. Those have impacts on the tornadoes, how they form. And so we really, to understand the tornado problem in the Southeast, we need to understand a lot more about that. The storm environment is different in the Southeast than in the plains. You're much closer to the Gulf of Mexico. The storms tend to happen more in the late winter and early spring months, when there's a lot more jet stream energy and a lot stronger winds in the atmosphere than in the plains. There's a lot of climatological differences. You can also have tornadoes with landfalling hurricanes, as we're seeing today in parts of the Southeast United States. So there's a lot of aspects to this that really need to be studied for us to be able to understand what's going on in the Southeast with tornadoes, and to be better able to predict and warn for these events and get people to respond to them. So in the early years of Vortex Southeast, starting in 2015, we really did a lot of work, kind of what we call risk reduction, where we were trying to figure out essentially how to do this sort of field work in the Southeast, so that we could organize some field campaigns and really start to look at building partnerships between not only NSSL, but academic partners, the National Science Foundation, and really come up with some approaches that would work in the Southeast. And after several years of that, we were able to come up with an approach that with a campaign that we felt like would be a good approach to really start getting to some of these problems that we were trying to investigate in the Southeast. And this the Perils campaign, which Mike and Tony are going to go into much more depth here, and how it studied the Rolling Fork tornado. But this was a field campaign over a 2-year period that was a joint collaboration between NOAA, NSSL, and the National Science Foundation. We had 9 observing periods, and were able to collect data from 28 different tornadoes using a variety of mobile instrumentation that ranged from mobile radars to UAS observations, mobile mesonets, which is what you see there, that truck up there. There was a lot of instrumentation, not just from NSSL, but from a lot of our academic partners. A lot of the academic partners in the Southeast participated, like University of Louisiana Monroe, University of Alabama Huntsville, and really to try to get very close range data from tornadoes in the Southeast, something that had never really been done at this kind of an organized scale before. And in the 2022-2023 period, we had a number of significant tornadoes that occurred during our observing periods, and this Rolling Fork-Winona-Amory series was the most impactful of the Perils campaign, and unfortunately, gave us a lot of data that we are going to be looking at for many years to try to figure out how to better predict and warn for tornadoes in the Southeast. And I believe with that, Tracy, I'm going to turn it over to the next group.
Great. Thank you so much, Alan. And as they're getting their slides ready, I'll just remind everyone that you can use the Q&A box. And after Tony and Mike finish, we're going to pause for questions, and then we'll pause for questions again at the end.
All right. Can you see the screen, Tracy?
Yep, it looks good.
All right. So my name is Dr. Tony Liza, and along with Dr. Mike Caniglio, we were the coordinating scientist and one of the principal investigators on the Perils Field campaign that Alan just overviewed, studying the physical science and meteorology behind tornadic thunderstorms in the southeastern United States. And so, to give you some idea as to how we deployed for the Rolling Fork tornado event, as part of Perils, we made the decision to deploy for the Rolling Fork event 4 days beforehand, all the way back on Monday, March 21st. This was kind of standard as to how we operated during the Perils project because we had so much equipment to take into the field and that had to be set up before the event even began for a given area. So we decided to go out 4 days beforehand, and we chose the lower Mississippi Delta region and the adjacent southern end of the Arkansas Delta and northern portion of the Louisiana Delta because we knew that was probably the region within our operating domain for Perils, for the Perils project, that was most likely to see tornadoes, and that we were most likely to capture data of a tornado in. So we went down there a couple days prior to the Rolling Fork tornado, began to set up our equipment, and you can see here in this map on the right, all these different dots and stars and X's are locations where we had different observing platforms set up, platforms such as mobile radars to measure the wind speeds and the rainfall and hail intensity within the severe thunderstorms and to detect the tornadoes and the tornadic circulations. What we call profilers to measure the atmosphere, measure variables such as the wind shear in the atmosphere or how unstable the atmosphere is. Different uncrewed aerial systems that can capture information not only on the atmosphere, but also can capture imagery of the damage. And we'll show some examples of that in our presentation here, using these uncrewed systems to fly over tornado tracks and get information that we can't necessarily get from the ground. Surface observation data, so we can look at temperature, humidity, wind speed, and direction, pressure right near the ground and see how that changes in proximity to a thunderstorm as it intensifies or as it's producing a tornado. So we had all of this instrumentation set up leading up to the formation of the Rolling Fork storm late in the evening hours on March 24th. So I'll hand it to Mike.
Yeah, so this is just an example of some of the specialized observations that we obtained that night and what we're analyzing. And this is from the NSSL Doppler wind LiDAR truck that is used to take measurements of the winds above the ground ahead of storms, much more frequently than what we've been able to do in the past on these projects. And we do that because we know that the winds above the ground, say in the lowest 1 kilometer or so of the atmosphere, are really important to understand for predicting tornado potential. So, but it's been traditionally something that's been lacking in a lot of our measurements in these field projects in the past. So this is something we wanted to make a focus of our efforts. So on the right here, just shows how we plot those wind measurements. And for those of you that may not be familiar with these, basically the points along the line represent the wind at different heights above the ground, and the wind direction is basically the position on the clock of the circle here, and the wind speed is represented by how far away you are from the center of that circle. So as this goes in motion here, something that we noted on this day is that right above the ground, at about 300 feet, which is where this line starts, the black part of that line. The winds were pretty strong pretty much all day from when we were observing. This is about a 7 or 8 hour loop, I believe, starting a little bit before noon. And we noticed that they became even stronger at 300 feet above the ground, about an hour before the tornado. And something else that was interesting on this day is that the change in wind direction and speed at that time actually happened pretty abruptly, within on the order of a few minutes and not gradually. And this is something that we're seeing in quite a few of our data sets across the Southeast with perils. And, this behavior of this very rapid change in the wind profile is something we'll continue to explore with all the other data sets that were obtained on this day.
All right, so in addition to studying the environment ahead of the thunderstorm, as the thunderstorm matured and produced the rolling fork tornado, we actually took a couple of our instrumented platforms and went into the storm to get measurements directly inside the thunderstorm as the rolling fork tornado was in progress to look at the features of the thunderstorm, such as the temperature, the humidity, the wind speed, and the wind direction and the pressure, and get a sense as to how similarly the storm that impacted Rolling Fork looked in these observations to storms that have been studied on the Great Plains, as Alan has mentioned, for a long time. So the picture on the far left here is an example of one of these, what we call mobile mesonet platforms that we run out of the National Severe Storms Laboratory, that captures these data. And we can actually drive around and use GPS correction to continue collecting data while we are in motion, including wind speed data, and then account for the motion of the vehicle. And the middle plot here, this animation, is the plot of the two mobile mesonets relative to the center of the parent circulation of the thunderstorm, what we call the mesocyclone, which is the larger circulation that can produce a tornado. And so the tornado is located just a little bit to the south of the star at the southern end of the mesocyclone, and then the star is at the center, and we can track the mesocyclone on radar. And so you can see how we came into the northern end of the storm over time, and then, of course, we didn't drive into the mesocyclone. We stopped at the northern edge of the mesocyclone to look for some key features within the supercell thunderstorm that produced the rolling fork tornado that we've observed in other storms on the Great Plains. And we've actually been able to, through the analysis that a student of ours, a student intern here at NSSL this past summer performed, identify several key features within these mobile mesonet observations in the temperature, humidity, and wind fields and pressure fields to the north and northwest of the apparent circulation and the tornado, as we were sitting in the town of Anguilla. And the tornado was moving out of Rolling Fork and into the rural areas to the northeast. So this is just one avenue, one example of research in terms of the actual storm itself and the parent circulation that we are investigating from the perils data set. Another example is from something we call the Mobile Lightning Mapping Array. This is a series of platforms run by the National Severe Storms Laboratory in Texas Tech University to study the characteristics of lightning within thunderstorms. And lightning, there's been a host of past research, can be a good estimate for the intensity of a thunderstorm. And if you look at the loop on the right, you can actually see the brighter colors showing up very quickly about halfway through the loop. And as it loops back, you can see it goes from the dark purple, and then all of a sudden you see the yellow start to pop up as the storm is crossing the Mississippi River into Issaquena County, Mississippi. And that's right about where the tornado forms. The tornado formed in the northern end of Issaquena County. So one of the hallmarks of the Rolling Fork storm is that it intensified very quickly after spending a long time maturing across the state of Louisiana in strength. It took a long time to form initially. Once it did finally become fully formed, a fully formed supercell in northeast Mississippi, it intensified very rapidly, produced the rolling fork tornado very rapidly. And once the rolling fork tornado itself formed, it intensified extremely quickly into the high-end EF4 that impacted the city of Rolling Fork. And after the event happened, we had all of our crews out in the field. We still had equipment that was out in the field that had been collecting data during the event. We also have some expertise here at the National Severe Storms Laboratory in assessing the damage, and this was a component of the Perils Field Campaign. One particular component of the damage assessment we were interested in was gaining more information on how to estimate tornado intensity in rural areas where there aren't as many structures to be impacted, because we use structural damage, and the enhanced Fujita scale is the main method for estimating tornado intensity and keeping records of tornadoes in the United States. So on the day after the Rolling Fork tornado, we had several teams go out. One team and I led performed a ground survey across the rural portions of Issaquena and Sharkey counties to assist the National Weather Service in Jackson, Mississippi. And then we also had other teams going out with the uncrewed aerial systems to start collecting aerial imagery of the damage across especially Sharkey County, where the damage was most severe. So I hand it to Mike.
So something that NSSL has explored in really the last few years or so is the use of UAS, or uncrewed aerial systems, or drones, in assessing damage from events that we observe intensely in the field as a complement to the ground surveys that Tony talked about and all the other meteorological data that we obtain out there. And we deployed these for immediately after the Rolling Fork event. And this just shows where we were. And we generally stayed out of the where people lived, partly because we didn't want to get in the way of the recovery efforts that were still going on there. But also, as Tony said, we think these assessments can help us better document tornado behavior in rural areas that usually aren't a top priority for those doing the traditional surveys from the Weather Service. And we deploy a few types of instruments here, or UAS. One of them is a quadcopter shown there, and this is just a pretty standard drone UAS for taking videos of the area that can be deployed quickly, that are then used to guide where we fly our fixed wing UAS that is used for a much more detailed mapping of the damage with the imagery that can capture details down to a few centimeters in the imagery. And that imagery is also precisely geotagged to allow for a very detailed analysis and orthomosaics of the damage of the event. So the black rectangles that you see here are where we were able to do the mapping using the fixed wing. Is actually out of all the tornadoes we've done over the years, I think this is probably the most extensive mapping we were able to do of any tornado. And I'll pass it back to you, Tony, to talk about some of that imagery, since he was up close and personal with a lot of it.
Yeah, so this is one example from the quadcopter system, as Mike described, over the northeastern end of the city of Rolling Fork. This is as far in as we captured any imagery into the city. As Mike said, we mostly stayed out of town, especially before the active search and rescue, search and recovery efforts had ceased. We waited until afterwards to gather any imagery. But this is some of the most intense damage. In fact, this is the most intense damage rating area across the entire Rolling Fork track. You can see that the single maximum highest wind speed was estimated at this structure here, which was completely blown off its foundation. And there were unfortunately several other homes that received high-end EF4 ratings along this side street here off of US 61, the Blues Highway. right here, cutting through the upper left corner of the picture. So this is just one example of the utility of being able to get a broader scale perspective on some of the severity of the damage over a given location using these uncrewed systems.
Yeah, so this shows a few examples of what we typically see when we take this imagery. We're typically out in the rural areas doing this, and we noticed right away that we can or at least not easily all the time, but in a lot of cases, it's much easier to identify the center line of the track when we get up and take this imagery, and to use that to assess fine scale tornado behavior here. And this is just one example of that. In this example, you can actually see to the right of the track here, where tornadoes spin cyclonically or counterclockwise. So we typically see tree damage on the right side of the path, pointed toward where the direction that the tornado was moving. But in this case, we actually saw very intense, and I believe Tony saw this out in the field too. He saw very intense tree damage pointed toward where the tornado was coming from, which isn't something that we typically see out there. And what we think happened is that this was such an intense tornado, is that these trees were blown down in the inflow jet to the tornado as it was approaching. They were blown down and pushed down so strongly that the winds, as the tornado was moving by, weren't able to even impact those trees. And I think that speaks to how intense this tornado was, and just gives you an example of the type of things we're able to assess by taking this real detailed imagery of strong tornadoes.
So another example of the utility of the UAS imagery can be shown here. This is an example about a mile to the northeast of the previous slide. This was an area we did a ground survey. This was one of the last ground survey areas that we surveyed from our team in Sharkey County before we handed off to the second Weather Service survey team that was surveying Humphreys County up through Silver City and into Holmes County. But from the ground, we knew that this had been an area that at least had a school bus that was left on an open property. We didn't know a whole lot more. There were some hints that there had been a structure there, some sort of structure on the property. From the ground, we saw what looked like remnant floorboards, perhaps. There was no poured foundation, however. It wasn't until we looked in the UAS that we noticed that below the school bus, something we couldn't see from the ground, there was actually an old trailer that had been sitting on the property also. We were able to see that and get a definition in terms of where the trailer was and where the school bus had landed on top of it, all nestled along the tree line that had been absolutely decimated by the tornado. And then as you exited this property to the northeast, looking at the UAS, we noticed this signature in the field in the imagery you can see here that we initially thought, upon looking at the UAS, was scouring or the digging of trenches potentially into the ground by the tornado winds. But then when we actually were able to finally get a team to walk out there once the soil had dried up, they went out and investigated this further and actually found that it wasn't trenching of the ground, but it was actually the trees that were impacted by the tornado being so thoroughly destroyed and pulverized that they were formed into this, what we call tornado mulch, for lack of a better term. But it was essentially granularizing the smaller branches and twigs from these pecan and bald cypress tree species that were primarily being impacted. And then the tornado was collecting this mulch and depositing it along the center, the core of the tornado track as it moved off to the northeast and away from the property. You can see here in the picture to the left that the mulch is primarily collecting in the lower portions of these planted fields. and then you can see a rather sharp cutoff to where the mulch was deposited on the ground, where if you look here towards the foreground of the picture, you don't see the collection of mulch. You also don't see mulch on the higher portions or the crests of the planted fields, because the mud from those crests was actually being scoured. The very top layer of the mud was being scoured by the tornado vortex. So this shows both the utility of the UAS and the utility, especially of combining the UAS information with ground survey verification and validation information to get a full sense of what was happening. And just for some perspective, when you see this sort of granularization of larger pieces of debris, such as tree limbs and twigs, it really is a sign of about as strong of a tornado as you'll ever observe. This is some of the worst pulverization, granularization of debris that's been documented in any sort of formal sense.
Okay, so I'll just finish up here looking ahead. We've touched on just a few examples here about what we're doing on the physical science side. It's a big one here that we touched on, and it really fits into a much larger research theme that we have ongoing at NSSL, and that's continuing to understand how storm environments evolve throughout the day and evening, and in particular, how rapidly that happens in these events, and how that can better our understanding of storm hazards and our ability to forecast them. And the rolling fork case was a great example of one of the cases that we can use for this purpose. And with the damage surveys, I think the ultimate goal here is to better estimate tornado intensity in rural areas from analysis of all the imagery we're collecting. And a part of that is also to try to understand how changes in land cover impact tornado intensity. And the Rolling Fork tornado for us was a gold mine of information for that, because of a large portion of the track that was surveyed, its intensity, and that we were able to see intensity changes in the damage patterns, or what looked to be intensity changes in the damage patterns that appear to be influenced by these changes in land cover and the surface roughness. Like what happens when you go from a plowed agricultural field into a patch of trees here, for example. And we're using these observations to help drive some very high resolution simulations of tornadoes to try to understand this behavior better. So just as an example. So I believe that's all we have here, and I'll send it back to Tracy.
Great, thank you both. Christiana, I'm gonna let you do the Q&A, and I'm gonna bring Alan back up on the screen too, just in use, so we have everybody.
Okay, thank you. And thank you so much, Mike and Tony, for that presentation. There were a couple of questions in the chat. They're both from Shernika Ferguson. The first one says, has Mississippi had the worst tornadoes? My dissertation research is on community resilience and the impact of disaster resilience in Mississippi. Is there any way I can reach out to someone to get data or connect for research?
I can start. So there are some studies that have been published in the past 20 years or so that highlight Mississippi as one of the states that has not only the most tornadoes, or one of the highest rates of tornado occurrence across the United States, but also is one of the most fatality-prone states, one of the most tornado fatality-prone states, if you use deaths from tornadoes as one way to measure the worst tornadoes. And of course, that a lot more goes into that than just the number of tornadoes or the intensity of tornadoes. There are a lot of socioeconomic factors that feed into that problem too. But we can certainly here at NSSL be a resource to reach out to get information and to point towards data that can be used in research. A lot of our data, all of our data, eventually is public, can be made public from field campaigns, and then we also can point towards other tornado-related data sets and whatever exists out there to help answer whatever questions people would like to research.
Anyone else want to add to that?
I think Tony covered it pretty well.
Okay. All right, her second question was, in terms of policy outside of risk management, has the state or federal government introduced any new policies regarding disasters or resilience?
I can take that. I think the answer to that question is not that I'm aware of. Uh, to the best of my knowledge, as far as I'm looking to just make sure I'm looking at the question again. Yeah, I mean, there's not really any that I'm aware of, any particular new policies lately regarding disasters or resilience. The structure of disaster response and recovery in the U.S. has been pretty stable for the last number of years. At the state level, I'm a little less certain because I'm not as, obviously there's a number of states. I assume she's referring to Mississippi. I'm not sure if they've done anything new as far as any new policies, but I'm not aware of anything based on the state level.
Okay, and would you suggest new policies based on your research?
Nothing comes to mind. I'll obviously let Mike and Tony jump in if they've got anything. I do think that one of the things that we're trying to study with Vortex Southeast is to try to better understand how structures are damaged, what sort of wind speeds are occurring near the ground, and whether or not, and that could potentially have some impact on things like building codes and how we build shelters, that sort of thing. But I think at this point, the research is still ongoing.
Alrighty. Have you looked into analysis of tree fall patterns as an additional way to estimate the tornado wind speeds?
Mike or Tony, one of you are probably more.
Yeah, I can start on that. So I've been on the periphery of some of that research here, but the answer to the question is yes. We have looked at something akin to what just reading the question. Some of our colleagues there, Chris and Frank, have done, where we can estimate, we can assume some sort of wind structure to the tornado that's idealized, and then and sort of model what might happen to the simulated forest or trees, and see how that matches to what we're observing. And we have done that, and we're actually collaborating with Western University, who has some models and has been working on that problem as well. And we're trying to integrate that into our estimates of tornado intensity. But and I'll mention one of the ways we're using the imagery that we're taking is to train it with machine learning algorithms to be able to identify the tree fall pattern, the direction of the tree, be able to quickly pull out whether the tree was snapped, whether it was uprooted, and you can see the root ball in the imagery. And the research on that is pretty promising to be able to do that very quickly with machine learning techniques. But again, that's something that's still not quite in its early stages, but it's not mature yet to be able to push along to the community yet.
And then just to follow up on what Mike said and add for the rolling fork case specifically, I know we've had some discussions within NSSL and our partners in using and looking at the aerial data from the rolling fork track, especially to do that sort of analysis in the rural areas outside of town where there are some more tree falls where that can be done. We've also had some discussions. We're investigating whether or not whether or not it would be possible to do that for the Amory tornado also, given how closely that tornado actually tracked to the Weather Service radar that serves Columbus Air Force Base in northeast Mississippi. That would make an interesting intercomparison case to compare radar estimation of tornado wind speeds to the tree fall pattern. So those are both sort of ideas that have already been discussed here at NSSL and we're investigating as potential avenues for research.
Thank you. Thank you, Mark, for that question. Destiny sent a question as well. She asked, did this study notice any wind patterns between Rolling Fork, Winona, and Amory?
Go ahead and try to take it. If I'm understanding the question correctly, I mean, the wind patterns in terms of the intensity, I'm going to try to answer this a couple different ways. In terms of the intensity, looking at the imagery we have access to, Rolling Fork was certainly the most intense of the three tornadoes. As Mike highlighted there were patterns in the damage that were very distinct with Rolling Fork, distinct patterns that highlighted the intensity. From the environment perspective, we actually have some observations of the winds ahead of the storm at several points in its life cycle, especially as the storm, Rolling Fork storm was passing northwest of some of our instrumentation at Yazoo City, Mississippi. And then the storm was in between the Winona and Amory tornadoes. It passed near a platform we had set up in Starkville at the Mississippi State University campus, just off the campus there at the airport. And then we had of course, the radar, as I mentioned, that serves the Columbus Air Force Base. And we could actually see as the storm passed by, changes in the wind profile, especially at Starkville and at Columbus, north of Columbus there. You could see rapid acceleration, rapid intensification of the wind speeds near the ground as the storm passed by, which we've seen again. Mike has done a lot of work on this in the Great Plains with data gathered in Great Plains supercell cases, showing the intensification of the wind speeds near the ground as especially tornadic supercells pass close by. So we do see all sorts of different patterns, wind patterns just within the tornadoes themselves and then in the environments near the storm as the tornadoes are occurring.
Thank you, Tony. And Mark said that multi-method comparisons are desperately needed. So that's great to hear. Daphne also had a question. She said, did the tornado mulch include recently living twigs, or was it all dead branches? The photo looked like the latter.
We took a look at that. So we had a long meeting with the National Weather Service in Jackson with other damage experts that occurred after the Rolling Fork tornado to figure out what the final intensity estimate was going to be for it. And that was a question that came up in that meeting. And our best judgment in terms of what we were able to collect from the ground is that there was a mixture of both. There was probably a little bit more dead than alive, but we definitely observed some live species too that had been destroyed like that, and that's not uncommon in these really, really violent tornadoes. This granularization of debris has been observed in the past also, and not just from trees, but from structural debris. But like we mentioned, this peak intensity, or this likely peak intensity of the tornado actually occurred northeast of Rolling Fork, where there were very few structures directly impacted.
Thank you. If you think of any other questions, the chat box will be open. Oh, I'm sorry, we have one more. They asked how much effect do you think the Mississippi River has on the cyclonic initiation?
Mike, do you want to take this or start?
Yeah, no, one of the things we are looking at in the southeast is how differences in land surface roughness can influence storm behavior, and we are seeing some evidence. I didn't show it here, but there was a study done using what we're calling copter sondes, and they're basically take profiles of the atmosphere. They can take wind profiles, temperature, humidity profiles. They just go up and down over a period of time, and from that analysis, we're seeing some evidence that the change in roughness, that as you go east of the Mississippi River Delta into the Pine Belt area in central Mississippi, might actually influence some of the environmental characteristics of the wind profiles very low to the ground, and might have some meaningful impacts to the cyclonic rotation that we see in the storms. But we think, in this case, we don't think that happened because that intensification to the storm happened west of where we would typically see that. So we think this one probably didn't have an influence from anything on the land surface and was more related to the very rapid changes that we saw in the environment.
Yeah, just to add to that, the Mississippi River itself, when you think about how big it is, I mean, obviously it's the longest river in North America, but it's rather narrow. So the impacts it's going to have as a storm moves from west to east across it will be rather quick, rather short-lived, and rather small. But as Mike said, you have that area there where you transition from the flat, open agricultural land of the Delta into the bluffs as you go out towards Jackson or Kosciuszko and areas up farther east. And in that transition happens over a broader area. And so you have a larger area of land surface where the winds could be affected in the environment. And then that could, in turn, have a longer time period to actually impact the storm.
Thank you. One more. Shanika asked, would you hypothesize that rural tornadic activity is more intense than urban tornadic activity?
That's a really good question. So back when he was studying tornadoes in the 70s and 80s, I know Dr. Fujita had sort of had that idea that an urban space could have a small impact on tornado activity, especially for smaller tornadoes. For a large tornado like the Rolling Fork tornado, it may not have as much of an impact. There's work that's been done on this question, though, is very limited overall, so we can't really definitively say one way or the other whether or not a rural area is going to have a more intense tornado impact than an urban area. I mean, for instance, with the Rolling Fork tornado, we mentioned it had its strongest peak in intensity northeast of town. In fact, in the middle of town, the damage was EF2 to EF3 intensity until you got to the northeast side of town. About the northeastern last half mile in town or so was EF4. But we saw that sort of fluctuation in the intensity of the Rolling Fork tornado in the rural areas as well. So we can't necessarily tie that sort of EF2, EF3 to EF4 intensity change to the city of Rolling Fork itself as more just probably being a product of chance.
Awesome. Thank you, Tony. So we're going to move to the next group, but if you have any more questions, please leave them in the Q&A box. If we have time at the end for more questions, we'll answer it there, but if not, we'll get to you via email. So we're going to move on to the next group. Thank you, fellas.
All right, hopefully those slides are up and in presentation mode. If not, let me know. But my name is Mackenzie Krojak, and I am the social science team lead at the National Severe Storms Laboratory. And I'm going to talk to you a little bit about the social and behavioral science findings from the 24th March 2023 event that we've been talking about. So first, I want to just describe a little bit about the post-tornado interviews that our team has been doing. In general, the goal with these interviews is the need to understand how forecast and warning information is being used to make decisions. So we want to know if the information is clear and actionable, if people trust the information, if they can make decisions using it. And then a little bit more specifically, we also want to know if that trust and understanding varies across different communities, or how they may vary by different event, depending on how the tornado evolved. Specifically for this event, we chose to look at this event because, like we've been talking about already, 3 tornadoes struck the area, resulting in 22 deaths and 225 injuries. There was also extensive physical science data that we just talked about. So to supplement what we're learning on the physical science side, we also want to understand, again, how our forecast information is impacting people. In addition, there is a wide disparity in access to public shelters, and we know that 16 of the 22 fatalities were sheltered in mobile and manufactured homes. So when we went out and did these interviews, we ended up talking to pretty much the entire communication chain, from NWS forecasters and broadcast meteorologists to emergency managers and then members of the public. In total, we talked to 11 weather service forecasters, 13 emergency managers, 8 broadcast meteorologists, and 26 members of the public. In general, the questions that we were asking were trying to understand different topics depending on who we were talking to. So when we were talking to weather service forecasters and broadcast meteorologists, we really wanted to understand what information they were trying to highlight, how they were communicating in the days and hours and minutes leading up to the event, including staffing and day of decisions. You know, were you bringing in more forecasters as the forecast ramped up or getting closer to the event? Or how did you make those decisions in general? When we were talking to emergency managers, we were specifically trying to understand their prior awareness of possible severe weather. So when did they initially become aware that this event could be impactful, or that the event was forecasted at all? We were also interested in what information sources they were mostly looking at. So where are they getting their information from? Is it generally the weather service, broadcast meteorologists, private sector meteorologists, etc.? And then what actions emergency managers were taken in the immediate aftermath of the event. And then when we were talking to members of the public, we were interested in their response capacity. So whether or not they felt like they could do something to protect themselves in response to this event, as well as, again, immediate event response and perhaps lessons learned or things that they would do similarly or different if they ever were to face an event like this again. So now, what did we learn when we bring this kind of all together? This is very preliminary, I will say. We are still in the middle of analyzing all of these interviews. But when we focus on professional meteorologists or the weather service and broadcast meteorologists, this event was predicted days before it occurred. And so it led to an increase of staffing for both the weather service and for media partners. In particular, when we talked to broadcast meteorologists, they said that those that were known for having a particular style. So, for example, in our local community here in Oklahoma, one of our broadcast meteorologists tends to wear like a sparkly tie, literally a sparkly tie, to indicate that today's a really bad day. Or there are other broadcast meteorologists who are known for wearing suspenders when it's a really bad day. So for those in the area that were sort of known to have a particular style, they were alerting viewers that storms were going to be bad, even if they weren't wearing that style. Like, you know, regardless of the cues, the visual cues that you're looking for, this is going to be a really bad day. So people were really trying to give this heads up in multiple different forms. Then, as confidence in this event increased, meteorologists were looking for a sort of next level, or a way to indicate that this event was particularly concerning to them. A couple quotes from our interviews. Our wording was more intense than usual. We recommended helmets and hard-soled shoes. And one of our respondents said, if you're watching from North Dakota and you have someone who lives here, call them, alert them, let them know. So they were sort of, especially on the day of the event, constantly trying to continue to ramp up that messaging. When we talked to emergency managers, they often look for those cues. So we're seeing meteorologists say that they're trying to give these cues that something's out of the ordinary, even for a tornado event, that this one is particularly concerning. And emergency managers pick up on those cues. They're looking for those things. Some of them that they mentioned were the moderate and high SPC level, as well as the wording and the tone used in weather service briefings. Pretty much all of our emergency managers that we talked to indicate that weather service briefings is the number one way that they get information about these events, and that they sort of get these cues or notifications that an event is out of the ordinary. And then they're also looking for personalized communication, like phone calls from the weather service. And this event made a huge difference. As soon as their jurisdiction was in the clear, so as soon as when they were watching the storm, as soon as they kind of knew that they weren't going to be hit, these jurisdictions immediately dove into mutual aid mode. So other towns and resources were rushing to the tornado path immediately in the aftermath. And this is a very organic neighbor helping neighbor system. They all, know each other, and they have communication strategies through statewide systems and even through NWS chat in Slack. They were using that to communicate who was going where. And okay, if this group is going to, the west end of the path, then I'll go to the east end, things like that. And then again, there's a huge disparity in resources between neighboring communities. So while some communities are really operating on a volunteer basis for their emergency management, others have multiple full-time employees and a full EOC. However, again, NWS chat helped those neighboring emergency services with more resources to the north and south of the paths respond immediately after the storm ended. One sort of interesting finding that I wanted to highlight was that while response immediately right afterwards is helpful, oftentimes these communities need long-term support more than anything. So there was a quote from one of our emergency managers. They said, I still have stuff in my shed right now because they don't have room in Rolling Fork. When they need it, I'll send it over to them. You're immediately flooded with material and water and cucumber Gatorade. I still have it. They said, no wonder they're giving it away. Cucumber lime Gatorade. There's 6 pallets of it sitting in their storage unit. So, while items and things might seem helpful in the immediate aftermath, oftentimes straight monetary support is more helpful. And then you don't have to store 6 pallets of cucumber lime Gatorade in the back shed. So just one interesting example of support that they received that may have been immediately helpful, but long-term support is also needed. I think if Cody is on, I'll pass it over to her for this one. Otherwise, I'm happy to do it.
Yeah, thank you. In terms of what we learned from interviewing members of the public, most were aware that there was a severe weather and threat that day, that there was a tornado watch that had been issued the day of the event. It was a Friday night. Many were at home, relaxing, streaming on Netflix as opposed to being tuned in to local television and gathering with friends and family. And as the storm intensified, it intensified quickly as it approached Rolling Fork. And this just resulted in many residents not making it to their preferred shelter location. Residents also reported getting information from their social networks. This helped them personalize the risk. And those that with less information heavily relied on some environmental cues, some of which involved sort of like creaking of their house, watching, the walls of their house move.
So wrapping up what we're learning from these interviews, obviously these are very specific to the Rolling Fork event. And unfortunately, we can't do these really in-depth, awesome interviews after every event. We are limited by our person capacity and just being able to be in the right place after these events happen. In addition to that, not everyone is ready to talk about their experience face to face immediately after the event happens. So one option that we are exploring and excited about is a post-event survey called Tornado Tales. It's hosted on the NSSL website, and it's an option for people to fill out a survey instead on their own time when they're ready to share that information, if they would like to share that information with us. So I just wanted to highlight this option. It takes 5 minutes in general to complete the survey. It allows you to share your story so that we can understand how information about these dangerous events is being used to make decisions, how this information perhaps could be tailored in a different way to help you with that decision-making process. So with that, I'll leave the QR code up there for a second, and thank you for the invite today.
Great. Thank you so much, Kinsey and Cody. And I think what we would like to do now is move into sort of some what's next? What does the future bring? So I'm going to just pull up each person, if that's okay. Let's see, and make sure that everyone has an opportunity to answer. So let's get, I'm going to see. We can get everybody up here. Okay, sorry, just 1 second. Okay. All right. And I want to just ask if they're in, like, let's start with the physical science side. How do you think the information that you Anthony, Tony, and Mike, that you share with us earlier is going to help to inform future watches and warnings? Like, I know there's some steps in there, but is that sort of the ultimate goal of collecting the information that you were speaking about earlier?
Yeah, I can go ahead and answer that. Yeah, I mean that's the ultimate goal here is we want to understand understand the atmosphere better, understand storms better, and transition that into a product or something that gives us the skill and ability to warn people in advance. More than we're doing so now, and that's a really difficult goal. It sounds good in a soundbite, but it's really difficult to take that physical science understanding, a meaningful increase in knowledge to tangible benefits to saving property and saving lives, and we think we see certain pathways for how that can happen on the physical science side, and that's essentially what drives the design of these experiments is verifying those hypotheses and verifying that it's true by going out there and taking these observations, and then updating our conceptual models for what's happening, but that's only part of it, really, and something that I've didn't really come into my career fully embracing or understanding is that's really only half of it. The next half of it is what Kenzie and Cody have talked about, and that's equally as difficult to get that into something that's actionable. So yeah, that's the ultimate goal here, and that's a very long process that we're working on diligently here. So yeah.
And to add to what Mike said, one of the big tasks, one of the big projects that we work on here at NSSL is information between the time a watch is issued and when a warning is issued, say for tornadoes or for severe thunderstorms, and how we can improve our ability to identify in advance the storms that are the biggest threats, and then how we communicate that. And that's where Mike and I, as the physical scientists, really have to we work in conjunction with like Kenzie and Cody and the social behavioral scientists to not only understand where the challenges in prediction are and predicting which storms are going to be the worst storms and which ones really need to be the focus of action, but then how to communicate that in between the time a watch is issued and a warning is issued. And rolling fork, for example, this idea that the environment can change as rapidly as it did ahead of the storm, and the storm itself can intensify as rapidly as it did before the formation of the tornado, is really an eye-opening moment for us on the physical sciences side in terms of where we need to better improve our understanding and our ability to foresee that rapid environmental evolution and the rapid storm intensification to occur, so that we can communicate that out in whichever way ends up being found to be the most effective. That's still something we're actively working on, and that environment and storm evolution is kind of a common theme across a lot of our perils data sets. We're seeing that a lot, that really it's about a 1 to 2 hour period in the environment ahead of a storm where the environment changes, and the response can be critical in terms of how the storm evolves. So that's really something that's going to be one of the key findings from the Perils Project overall, is identifying those rapid changes and how they occur.
Thank you both for that. And that's kind of a good segue to a question I had for Cody and Kinsey about, do you think there's any risk communication messages that, could or should change as a result of this study, or maybe some other studies that you've, been involved in?
Yeah, I think I'll echo a little bit what Mike said about it takes time and, multiple studies to sort of come up with a wholesale change that we might want to make. However, I do think we're seeing a lot of indication that perhaps the warning is not enough time for some people to be able to respond effectively, those who may have to leave the structure that they're in to safely shelter from a tornado. And on the flip side of that, sometimes our watches are almost so good that they are, 4, 5, 6 hours in length before you see a storm. And so that may be too much time. So maybe I don't want to leave my house for the entire day, for example. And so I think we're starting to see some indications that there could be usefulness in, like what Tony said, a between watch and between warning messaging product or strategy of some sort, where we can alert folks who want that additional time to respond before a storm impacts them. Now, of course, we do have to think about, if it's possible to do that for every storm, and if it's not, that leaves us with a lot of questions about if people are expecting that type of messaging and we don't provide it, what that really means. So those are some initial thoughts for myself, but yeah, these studies are really leading us to better understand what people's needs are and how we can tailor our messaging styles to help meet those needs. Cody, I'd love if you'd add, if you have things that I missed there.
I think there are also some potential technology changes in the future with television. They're currently discussing the next broadcast standard. If folks remember when we went from analog to digital, there's a discussion of a developing standards for a new digital standard called ATSC 3. And it could, given, the number of folks that do stream and watch less cable and antenna television these days, that could open the door for alerting to happen from devices like televisions that are newer and equipped with the ATSC 3 receiver. So I think that could also help change the way folks are receiving information and possibly tailor it more to their personal location and help personalize that risk in the future.
Thank you. And just one follow-up question I had. I've noticed that like when Christiana and I are out in the field, sometimes people will talk about how they're waiting for the broadcast meteorologist to say like the name of their street, before they take cover. And I just wondered, in like your research, if you have come across any similar things where maybe the expectation doesn't always match what's possible.
Oh yeah, we're seeing that quite a bit in a number of different events, that people really want to know that they themselves are going to be personally impacted. And from my perspective, I don't think we're going to change that. That's sort of a natural human process when we're making decisions. There's a cost to sheltering. There's a cost to making all the decisions we make. And so we're constantly weighing the pros and cons in our head. And I'm not sure we're going to change people's, natural affinity to want to really personalize the risk. So I just want to highlight the importance of what our broadcast meteorology partners are doing, right? They're really taking the information that is sort of a little bit more broad on the Weather Service side, and they're boiling it down to something that is really personal and something that people can relate to. And the value of that cannot be understated.
I will say, on a personal note, I have a daughter that's of age to stay home alone over the summer, and that was actually a conversation that I had with her of like, I expect you to be the weather aware one of your friends, and if you find yourself in this situation, these are the landmarks you need to listen for, and if you hear them, then you better be in someone's house in a safe location.
Yeah, I love that. Just making sure that, folks have this more, realistic of like, what is my responsibility in all of this? So I think that's great. So thank you. Christiana, I'm going to switch to you for just a second and see if you wanted to see if we have any questions in the chat box.
Thank you, Tracy. Yes, we do have one question in the chat box. And they wanted to know, I'm sorry, how did you know that a tornado would hit Rolling Fork? And how were you able to set up all the equipment ahead of time? How far in advance did you predict the tornado was coming?
So we had to decide to deploy on the system, the storm system that produced the Rolling Fork tornado 4 days ahead of time. It was even a couple days before that we knew that there was going to probably be a potential for tornadoes in the southeast United States. We didn't know for sure it was going to be Rolling Fork or even Mississippi at the time, but we knew it was going to probably be somewhere in the southeast United States. One of the things we look at the jet stream, and how does the jet stream look? And in preparing for this, I was actually digging through some old files I had saved from the Perils project, and I actually found a comparison I had side by side of the Rolling Fork trough, the forecast 4 days beforehand when we made the call to go out, to the April 27th, 2011 outbreak, the infamous super outbreak. And there were some differences, and obviously this was not a super outbreak. We didn't have 15 tornadoes of EF4 or EF5 intensity, but we had one really big one. And so there were some differences, but the jet stream disturbances that produced the storms looked fairly similar, and similar enough that I saved a side by side on my computer, and it's still in a folder there. Is something that just kind of stuck out to me at the time. And there, we had a lot of discussions, those of us involved in the Perils project, from basically the time we made the decision to go out until as we were driving out to the Mississippi Delta and so on, that we knew this event had the potential to do something really, really bad. In fact, I think I said there was a colleague I was talking with, and I said, if we observe a violent tornado in the Perils project, this is going to be the system that's going to do it. And the lower Delta region, it was very clear by 2 days beforehand, even that was the highest probability area for that to happen. When we had the discussion in terms of where within our operations area we were going to go, it was unanimous, which for a group of 30 scientists is almost never the case. We can never agree. Everyone has an opinion about something. In this case, we all had the same opinion, and we were going to the lower Mississippi Delta. So we knew days in advance that this was, I mean, the National Weather Service forecasters knew days in advance that this had the potential to be a bad, bad day. And unfortunately, it became a bad day. What was almost a little bit surprising to us was that it held off within the day of as long as it did. There were a couple initial storms in the heart of the Delta and in southeast Arkansas that we thought had the potential to become tornadic and produce large tornadoes, and they were struggling. And there was a while there that afternoon, we were kind of, in the early evening, we were kind of wondering, was this event really going to pan out? We were hoping it wouldn't, because obviously the potential for something really bad to happen was there. But then we identified the Rolling Fork storm. I know our crews identified. Mike took a balloon, launched a weather balloon before 7 p.m. that caught basically everyone on Perils' attention because it captured the environment change that we talked about. It was the first observation we all kind of took notice of, that this environment change was occurring. And we saw that weather balloon in conjunction with the storm that was forming in northeast Louisiana. And that's when, like, our crews one of the crews I was, leading in the field, that went after the storm itself, went into the storm. That's when we decided to go for it about an hour beforehand. That's when we said that storm is moving into an environment that's extremely supportive of tornadoes at this point. And we don't know that it's going to do it for certain, but if any storm tonight is going to do it, that's going to be the storm. And that, unfortunately, is what happened as soon as the storm crossed the river into Sequina County.
Thank you. How is your research inclusive of vulnerable populations?
That's a fantastic question. So one of the things we're really thinking about in terms of tornado events is who is most vulnerable to injury and loss. And one of the populations we've identified for tornadoes is mobile and manufactured home residents. And so we are particularly interested in understanding their decision-making process. And again, over the past few years, we've really dove into this idea that 15 minutes or so with a warning is not enough time to get to a safe place if you live in a mobile and manufactured home. On the other hand, it's really unreasonable to ask someone to leave hours and hours and hours before the event will even begin. So we are particularly interested in studying vulnerable populations to tornadoes, and we take special care to make sure that we are getting those perspectives in our data. But I will say it's not an easy task. And so we're always open to hearing other suggestions to make sure that we're serving those populations.
I'll also add that we have a Latina graduate student and former graduate student and now colleague, because he has moved on to a postdoc. He is also Latino. And they have focused their research on Spanish-speaking populations. So they have gone and done some interviews with Hispanic communities in primarily the Mayfield tornado that was in December of 2021. So that is another vulnerable population that we have focused on in previous studies, not this study, but previous.
Thank you. Kenzie, I believe this question is directed to you, but if anyone else wants to add anything, you're welcome to. They asked, do you find any perception difference between Oklahoma and Mississippi on tornadoes?
Yeah, that's also a really good question. We do generally see a few differences in the way that people understand their risk for tornadoes based on where they live. Actually, one of the largest indicators of whether or not, they are confident that they'll receive warnings or respond is actually whether or not they've received a warning before. And so something that we are interested in is understanding how we can improve people's capacity to receive and respond to warnings without exposing them to warnings and dangerous events. So that's of particular interest to us. And then I think the second question about having local assistance, I'm sorry, Christiana, if I'm jumping the gun there. But asking about local assistance in conducting our surveys, we were lucky enough for this event to have Tracy and our partners at the Mississippi-Alabama Sea Grant Consortium help us out with that data collection. Now, that doesn't always happen because we don't always have partners for every tornado that we look at. But for this one in particular, we did have local assistance in that capacity. Apologies for jumping the gun there, Christiana.
No problem. What about on the physical science side? Did you have any local assistance in conducting your surveys, such as Mississippi Emergency Management or MSU Extension Services?
So the damage surveys are a little bit different because they happen immediately after the event. So the emergency services and emergency management are frankly busy with the search and rescue. In fact, when we were doing the damage surveys in Sharkey County, there was still active search and rescue and search and recovery going on in the city of Rolling Fork. So we stay out of their way. We make it our business to stay out of their way and make sure that we don't impede any of those efforts, those critical efforts that are occurring. So we get as much information as we can without being a hindrance to the important, life-saving, life-preserving efforts that are taking place in the immediate aftermath. But in terms of the project itself, not so much in the surveys, but in the actual data collection, we had a tremendous amount of local help. So years of planning went into perils. And one of the big aspects of the planning was finding locations to put instrumentation. Alan mentioned in his overview how difficult it is to study severe storms in the Southeast because of hills and terrain and the higher population density, the challenges the storms themselves present, that they move faster, and a lot of them happen at night, as the Rolling Fork tornado did. So we to counteract a lot of those challenges, we spent years finding sites to deploy mobile radars, the mobile lightning mapping array equipment. A lot of those mobile LMA sites were housed on private property where the scientists who used that equipment and were deploying that equipment reached out to local residents and got their permission to set up, and would set up that equipment the day before an event and take it down the day after. We had other instrument platforms that did the same also. So there was a lot of engaging the local community and with local residents just in the data collection itself, even outside the damage surveys. In fact, we had one mobile LMA site in the city of Rolling Fork at the Sharkey-Issaquena Academy, where the scientists contacted the academy officials and got permission to use that as a deployment site, and it was there when the tornado hit. So we didn't engage so much with the local community. We did engage with the National Weather Service, as I mentioned. We coordinated with them on the damage survey for the Rolling Fork tornado, so that not only were we out getting scientific data, we were also able to supplement and help them since they had so much damage in their communities. But in terms of the local community, for us on the damage survey side of things, it's a little different because oftentimes there are higher priority issues that local officials are addressing.
Thank you so much. And unfortunately, we are at time. So Destiny and Shanika, keep an eye out on your email. We will answer your questions there. Mark, you as well. But we're going to go ahead and wrap up. Tracy, did you have any closing remarks?
We just appreciate everybody being here today. Thank y'all so much for sharing with us. This was amazing. I learned a ton today. So thank you for spending time with us, and we'll make sure the recording gets to everyone. If you have any questions about the outreach and engagement pieces, please contact Christiana or myself. And again, we'll get to these last questions that were put in the Q&A box. We have your email addresses from where you registered, so we will ask our experts here and we will get back to you. So thanks everyone, and we hope you'll join us again for a future webinar. Have a great afternoon.